Welcome to this video on microelectromechanical systems, or MEMS. MEMS devices operate in the microscale, where features are measured in micrometers and nanometers. Microscale engineering enables macroscopic functionality. The genesis of micromechanical miniaturization started with Richard Feynman's concept in 1959. In 1965, the prototype was developed with the resonant gate transistor. The inflection point came in 1982, when silicon was proven as a superior mechanical material. MEMS is the intersection of integrated circuit batch fabrication and physical micromachining. The goal is to leverage the efficiencies of the microelectronics industry for complex electromechanical systems on a single semiconductor substrate. The physics of miniaturization involves scaling laws. In the macro world, volume-dependent forces dominate, scaling with L cubed. In the micro world, surface-dependent forces take over, scaling with L squared. The most profound metric is the surface-to-volume ratio. At the microscale, electromagnetic actuation fails due to poor scaling of magnetic forces and thermal limits. Electrostatic actuation dominates, relying on surface area rather than volume, and scales well, consuming near-zero steady-state current. MEMS utilizes a variety of materials. Single crystal and polysilicon are standards. Materials like silicon nitride and silicon carbide offer superior properties, such as high electrical insulation and thermal resilience, while polymers like SU-8 are used for microfluidics. Piezoresistivity is a form of solid-state transduction. It relates to a change in electrical resistance due to mechanical stress. This change is caused by geometric deformation in metals, but by intrinsic resistivity change due to band structure shifts in semiconductors. Piezoelectricity involves a direct effect, converting mechanical stress to an electrical charge, and a converse effect, converting an electric field to mechanical strain. The industry is shifting from PZT to aluminum nitride for CMOS compatibility and high performance. Electrostatics is another solid-state transduction method. The attractive force between parallel plates is governed by this equation. This force shows severe nonlinearity, increasing proportionally to the inverse square of the remaining gap. The pull-in instability describes the collapse of a movable electrode towards a fixed electrode. In analog devices like mirrors, this phenomenon restricts continuous motion. However, it is exploited in digital devices, such as RF switches, for rapid closure. Stiction is the catastrophic adhesion of compliant microstructures, driven by forces like van der Waals, hydrogen bonding, and electrostatics. These forces become dominant at the microscale, especially when gaps are below 100 nanometers. Stiction mitigation involves chemical passivation, like using self-assembled monolayers to reduce surface energy. Topographical solutions, such as Wenzel's dimples, and process solutions, like supercritical CO2 drying, are also employed to eliminate attractive forces. At the extreme edge of MEMS, quantum and thermodynamic limits are encountered. The Casimir effect is a quantum force. The fluctuation dissipation theorem and thermal creep represent fundamental thermodynamic limitations on sensor resolution and flow dynamics. Microfabrication employs two primary methodologies. Bulk micromachining is subtractive, using deep reactive ion etching to create high-mass, rigid structures. Surface micromachining is additive, building and releasing complex layers on top of the wafer. MEMS is a multidisciplinary field, synthesizing solid-state physics, nonlinear mechanics, materials, science, physical chemistry, and microfabrication. Macroscopic intuition fails at this scale, requiring a deeply interconnected approach to succeed.
We are architecting the 1 cubic millimeter synthetic sensory organ, which involves engineering the intersection of physics, chemistry, and distributed computing. Operating at the millimeter scale nullifies traditional Newtonian engineering. As volume drops faster than surface area, gravitational forces become negligible. The sensitivity and noise paradox shows that as mass approaches zero, the noise floor spikes. Engineers must maximize the mechanical quality factor or utilize carbon nanotube piezoresistors to solve this bottleneck. The RF communication bottleneck is defined by the Chu-Harrington limit. The electrical volume of an antenna drops below lambda over 2 pi, and most input power is reflected back rather than radiated. We can escape the RF trap via passive optics. Compared to active steered lasers, passive corner cube retroreflectors offer ultra-low power physics for data transmission. Smart dust requires specialized MEMS techniques integrated with VLSI semiconductor processes. This involves bulk micromachining, surface micromachining, and advanced 3D topographies like atomic layer deposition. Smart dust replaces bulky laboratory spectrometers with precise molecular recognition elements bound directly to the sensor surface, enabling chemical mapping and quantum sensing. To address the ecological paradox of persistent silicon nodes, the solution is to use degradable intelligent radio transmitting sensors, or DIRTs. These employ bio-based polymers like PLGA/PLA. Surviving the environment means combating the triboelectric threat. Colliding silica dust generates a localized electrostatic charge that causes triboelectric current to bleed into the sensor, corrupting data. To survive on a less than 1 nanowatt standby budget, the architecture of a nanowatt brain requires sub-threshold voltage scale, custom 8T/10T SRAM, and switch capacitor networks for power management. Ambient energy harvesting modalities include photovoltaic, piezoelectric, electromagnetic, and electrostatic or triboelectric methods. Recent advances utilize hybrid generators for energy scavenging. For the operating system, TinyOS is the solution. It uses an event-driven architecture and a single shared memory stack written in ESC to eliminate context switching overhead. Swarm intelligence and distributed routing are crucial, as a single dust mode is useless. We look at Leech for hierarchical clustering, Pegasus for chain-based aggregation, and directed diffusion for data-centric routing. By 2026, smart dust will achieve commercial reality in areas like defense and aerospace, industrial heavy machinery, and biomedical implants and edge AI. The final frontiers include achieving absolute power density, solving the challenge of microscopic spatial localization, and bridging the gap in the privacy paradox posed by mass deployment of covert sensor networks.